A prime number is a counting number with exactly two counting number factors. A composite number is a counting number with more than two counting number factors. A factor is a number to be multiplied. Here's an example. 2 times 5 is equal to 10. The 2 and the 5 are being multiplied, so they are the factors, and the 10 is the product. Here's another example. 4 times 2.5 is 10. The 4 and the 2.5 are factors, and the 10 is still the product. But when we talk about the factors of 10, we say that the factors are just 1, 2, 5, and 10. Because typically, when we talk about the factors of a counting number, we mean just the factors which are counting numbers. In fact, this assumption is so prevalent, many definitions of prime number don't even mention counting numbers. The definition of a prime number is often a number with exactly two factors. And the definition of a composite number is also a number with more than two factors. Here are the factors of 10 again. And now here are the factors of 12. 1, 2, 3, 4, 6, and 12. And here's a third number. 28. The factors of 28 are 1, 2, 4, 7, 14, and 28. We can find the factors of any counting number. And you may have already noticed that 1 is always a factor of a counting number, and the number itself is always a factor of a counting number. All of the factors of a counting number except the number itself are called proper factors. And getting back to the number 10, it is called a deficient number because the sum of its proper factors is less than the number itself, which is 10. And here we demonstrate 1 plus 2 plus 5 is 8. And 8 is less than 10, so 10 is a deficient number. Let's try 12. Well, that's an abundant number because the sum of its proper factors is greater than 12. 1 plus 2 plus 3 plus 4 plus 6 is 16, and 16 is greater than 12. And the number 28 is special because it's called a perfect number. And the sum of the proper factors of 28 is exactly 28. 1 plus 2 plus 4 plus 7 plus 14 is equal to 28. Perfect numbers are far apart. The next perfect number is between 100 and 1,000. The number 1 has just one factor itself, so it is neither prime nor composite. All other counting numbers are either prime or composite. 2 is the only even prime number. Its factors are 1 and 2. And for any other even number, say n, that happens to be larger than 2, the number must have at least these factors, 1, 2, and the number itself. So that tells us that except for 2, all other even numbers are composite. And now we're going to use this method from a long time ago called the sieve of Eratosthenes to find prime numbers up through 99. We've placed our counting numbers in rows of 12. You will often see the sieve of Eratosthenes with the numbers placed in rows of 10, but I chose 12. And the first thing we're going to do is look at the smallest number, which is 1, and we know that it's not prime and it's not composite, so we cross it out. Then we look at the number 2. We know that it's prime. And then we realize that all other even numbers are not prime, and because of the way we've arranged the numbers, the even numbers are all in columns, so we cross those even numbered columns off. Then we look at the number 3. 3 times 1 is 3. It's clearly prime. And now we're looking for other multiples of 3. Well, some multiples of 3 are even. But you can see there's 2 more columns of numbers which are multiples of 3, which happen to be odd. And that's why we arranged our numbers in rows of 12, so that the 3's would all line up in the same column. 4 has already been taken care of, therefore all multiples of 4 are taken care of, so we go to 5, which is prime. And we know that numbers that end in 0 or 5 are divisible by 5. Well, the numbers that end in 0 are even, so they're already crossed out. A few of the numbers that end in 5 are also divisible by 3, so they're crossed out. So we go through and we look for other numbers that end in 5 that haven't yet been crossed out, and we cross them out. And that brings us to 7. 7 doesn't have nearly the nice, easy rules and patterns that the first three numbers we looked at do. So we just count by sevens. Well, many of the sevens have already been taken care of. But we know that 7 times 7 is 49, 7 times 11 is 77, and 7 times 13 is 91. So we found three more numbers divisible by 7 that we crossed out with purple X's. And now we know we can stop. And while we don't have time for the proof, it turns out if you're trying to find the prime numbers from a certain number or less, once you've tested all of the numbers up to the square root of the number, you can stop testing. And if we go to 100, which is 1 bigger than 99, we know that the square root of 100 is 10. And we've tested or crossed out all of the numbers through 10. So the next number, 11, which is prime, it turns out all of the subsequent numbers divisible by 11 have already been crossed out. If we were trying to find more prime numbers, the number 11 times 11, which happens to be 121, would not be crossed out yet. But since we're not going that high, we've already gotten all of the numbers that are divisible by 11 through 99. So the rest of the numbers have exactly two factors. They're prime, and we circle them as shown. And it turns out there's 25 primes less than 100. And here's a list. If you'd like to copy the list, you should just stop the video, and you can copy down the list of 25 prime numbers. Expressing a number as a product of primes is called the prime factorization of a number. One method of finding the prime factorization is called a factor tree. Here's one for 24. We think of two numbers that multiply to make 24, 4 times 6, and we realize neither one of those is prime. So we factor further. 2 times 2 is 4, 2 times 3 is 6. Now all the numbers at the bottom are prime. And since we don't use ones in factor trees, and we also don't use ones in prime factorizations because 1 is not prime, we're done. Almost done. We usually write prime factorizations using exponents as shown. 2 to the third times 3 is the prime factorization of 24. And then you might ask, could it be done another way? Yes. 3 times 8 is also 24. Now the 3 is prime, so we just recopy that. The 8 is not prime, so we go to 2 times 4. But the 2 times 4 includes a number which is not prime, the 4. So we have yet another set of branches of this tree. But our final answer, while in a different order, is still 3 2s and a 3, or, using exponents, 2 to the third times 3. Now we're going to try another method. I call it, and many people also call it, upside down division. Generally start with the smallest prime that I think it'll work, such as 2, and divide upside down because it usually can be done quickly without showing a lot of work. 2 still works, and 2 works one more time, leaving me with 3. And then the numbers along the left, that's my prime factorization. I'm glad it's the same answer we got when we used the factor tree method. Here's the year that this video was recorded, 2013. Now, if you know anything about divisibility, you can add up the digits, and they equal 6, so we know it's divisible by 3. So we'll divide by 3 upside down. And if you know anything about division, that's not that difficult. But now it gets a little sticky. It's sometimes hard to tell what might be next. Sometimes a calculator helps, but it turns out 11 works. And then you divide by 11 and you get 61. And then when you recognize 61 as a prime, you know you're done. And here's a prime factorization where exponents are not needed because there's 1 3, 1 11, and 1 61. 3 times 11 times 61, the prime factorization for 2013. In this lesson, we looked at several terms: factor, prime number, composite number, proper factor, abundant number, deficient number, perfect number, prime factorization, and factor tree.